So we have our three ocean layers: our surface layer, which is mixed by wind currents and surface currents, our intermediate layer, which is where our thermocline resides, and our deep layer, which is uniform and cold. Here we can see how these things are affected by salinity and temperature and density of the seawater, and also how they change in polar parts of the ocean versus the tropics, and also seasonally. So in the graph up here, we can see depth, salinity, temperature, and density. The surface layer, you can see, ranges from 33 to 37 parts per thousand, and that all goes down to about 35 parts per thousand in the deep layer, so very uniform. For temperature, we can see a big thermocline here. So surface layer kind of changes depending on where we are and also the seasons. And then our intermediate layer is where our intermediate layer is where our thermocline is. And then we can see our uniform 4 degrees in the deep layer. Our density will increase, right? Because salinity and temperature can affect density, with an increasing density as we go down into our deep layer. If we zoom in on temperature and we look at the tropics, the temperate, and the polar regions, which you can see here with these different lines, you can see the polar region has less of a thermocline. The temperate region also has less of a thermocline, and it's the tropics that has the biggest thermocline, especially through the intermediate layer. And this is because it's so warm on the surface layer and has that big thermocline and then that solid deep layer that's stable. Zooming in on this top part again, you can see that seasonal thermocline in the summer, right, for our surface layer, and our permanent or main thermocline in the intermediate layer. And again, that stability of the layers really depends on density differences and seasonality. So the bigger the density difference, the more energy it takes to mix those layers. And so what this means is that in the polar regions where there's not a huge difference, there's downwelling during different seasons, and that can, turn water layers over. Downwelling is essentially when cold water starts to sink. And so you can see that through the sun. This is an example of the polar area. So you can see, in their summertime, lots of sunshine. In their autumn time, you can see the thermocline decreases, things get a little stormier. And then in the wintertime, you see that downwelling of the surface layer. This is really important because it allows replenishment of oxygen and pushes ocean circulation. So we consider big scale currents to start their circulation in the cold parts of the ocean. So again, because of variability in temperature and salinity, water masses have these features that can be tracked. And thermohaline circulation is what drives big currents, the deep water currents. Thermo meaning temperature, haline meaning the amount of salt. And so this is our ocean conveyor belt. This is a deep water current that basically takes around 4,000 to 5,000 years to completely cycle all of the different oceans. And it starts in the poles. So it starts up here in the North Atlantic or down here in the Antarctic bottom water. And that cold water moves along towards the equator and then comes up as it gets displaced by water coming in behind it. This is what we call the Great Ocean Conveyor, and it creates a big overturn of water, again, that starts in the North Atlantic and Antarctica, and brings oxygen to the depths and also greatly influences our climate. Again, all of the videos that are shown here are in your module, and I really highly suggest that you watch them. Let's talk about waves. So wind is also the cause of not just surface currents, but also waves. What's really cool about waves is that the waves that you see crashing on the shoreline were actually created thousands of miles out in the open ocean. It's actually energy that's flowing through water. Water is just the medium that is moving or transferring this energy, essentially. And the energy comes from the wind. A wave has different parts to it. The highest part is called the crest, and the lowest part is called the trough. And the wave height is the difference between those two things. The wavelength is the distance between either two crests or two troughs. And the period is the time that passes between the wavelengths, essentially. And so here's the anatomy of waves, right? So here's the deep part, the trough. Here's the top part, the crest. And between two crests would be a wavelength. And the time it takes from one crest to another to pass through a stationary point, for example, 15 seconds, this would be the period. Now, waves, again, they're not necessarily the vertical movement of water. They're not necessarily the horizontal movement of water. They're actually the vertical movement of water. This is why out in the ocean, when you see, boats bobbing up and down or birds bobbing up and down, if the water was actually moving towards shore, then all the surfers, all the birds, all the boats would eventually make their way back to shore. Instead, the particles of water are moving vertically, and they're actually moving in little circles, and that's what creates that wave-like pattern on the surface of the water. So water is moving up and down in these circles, and that's what creates that bobbing effect. The energy is what's moving through the water. And the wind, so the energy is created by wind blowing across the surface of the water. The wind has energy, and through friction, some of that energy, kinetic energy, is transferred to the water. That starts the water moving, right? It creates what are called seas, okay? And that's where you get the energy moving through the water. The length of time and the area that a storm or wind is blowing over the surface of the water can affect how big the waves or the swell is. So this is what we call fetch. Fetch is the area upon which the wind is moving across the water. So the larger the area of the storm out in the open ocean, the larger the waves. Likewise, the longer the wind is blowing, the larger and longer the swell tends to be when it reaches our shores. The smaller the area, the smaller the waves. And that's just basically because the energy not as much energy is being transferred into the water in a smaller area. So the more energy that is transferred, the larger the wave. The first thing that's created are seas. And the higher the wind velocity, the larger the fetch, the longer the time that blows, the greater the opportunity that these wind waves have time to combine and grow into organized swell. And this video, which also is in your module, is a great explanation of how waves form. This is an important figure because this describes how what happens in the ocean open finally ends up as swell and surf on our shores, like for example the north shore of Oahu. The wind or the storm is blowing across the top of the ocean, transferring energy into the ocean, creating seas. Enough of that energy is transferred and starts moving through the water molecules, creating that vertical motion of water particles. Essentially, that energy gets organized into swell. Eventually, that swell will reach a shoreline where it hits a shallow coastline, like the North Shore, and the water molecules that are moving usually vertically all of a sudden start to kind of feel the bottom or feel friction from the bottom. And that causes water to get pushed up and actually move up and over to create surf or breakers on the shoreline. And that's what creates our surf here everywhere. So what about tides? Tides are all about gravity. Tides are influenced not just by the moon, but also by the sun. But the moon, because it's much closer, has a much larger pull on the water in the ocean. Excuse my cat. Gravitational pull creates an equal and opposite force or bulge of water facing the moon and away from the moon. The bulge of water away from the moon is created by centrifugal force because that's what's being applied to a rotating body, i.e. the moon. the Earth is essentially just rotating underneath these two bulges. And that's where we get high, low, high, low. And this is why in many places around the world, we have two highs and two lows, and they alternate, high, low, high, low. So the moon and Earth share a common center of mass, and their rotation around the center creates those two tidal bulges. The sun also has an effect because it's so massive that it creates a pull as well, although it's not as strong as the moon. And as you guys know, the moon orbits around our Earth, and the Earth rotates around its axis. But the moon does so even though it takes the Earth 24 hours to rotate around our axis, the moon cycle moves a little bit every day, right? It takes about 28 days to move completely around the Earth. And so this is why every day the tide comes about 50 minutes later. So again, here you can see the Here you can see the stationary flag, right? And you can see like at, midnight, we've got the moon, we've got a high tide, so we're under the high tide bulge. 6 hours and 12 minutes later is our low tide. And then you do another 6 hours, 12 minutes, and we'll have this be under the second bulge, the high tide. Another 6 hours, 12 minutes, our second low tide. And that whole time, the moon is also rotating or orbiting around our Earth. And that's what creates the shift in the bulge. And so that's why it takes a full 24 hours and 50 minutes to get back to being under that same high tide mark we were at the beginning. Now, the sun influences the intensity of the tides. When the sun and the moon are aligned, we get what are called spring tides. These are really, really big, usually big highs and big lows because the bulges become more pronounced. And so you'll usually see spring tides during a new moon and during a full moon, when the sun, earth, and moon are all in straight lines. Neap tides are when the sun is at right angles to the moon and everything, it kind of cancels each other out, so you don't get the biggest bulge. And so you can see the influence of the sun creating the neap tides during the first and third quarter. Real world tides obviously are more complicated because there's continents and other features of the sea floor that produce all these different tidal cycles. There's 3 common tidal cycles: semidiurnal, mixed semidiurnal, and diurnal. Semidiurnal means 2 equal highs and 2 equal lows per day. Mixed semidiurnals means a low high, a high high, a low low, and a high low per day. And then a diurnal tide is just 1 high and 1 low per day. Based on this tide chart of 24 hours in a day, what kind of tides do you think Oahu has? If you guess semidiurnal, you're right. There's our high high, here's our low high, here's our high low, here's our low low, and here's our high low. And that ends it for our chemical and physical properties of the ocean. That was a big chapter with a lot of info. I really encourage you guys to watch a lot of those videos for extra explanations. Usually in class I would show those, but I can't show them on these videos here. So I really encourage you to fill out your Chapter 3 study guide, watch those videos, and let me know if you have any questions.